All right, hi everyone. It's a pleasure to have Ross Akhmechet this week at our seminar to tell us about his construction of the equivariant annular Khovanov homology. Thanks, Ross.
Thanks everyone for coming. Thanks for giving me a chance to speak. So I'll talk about this preprint from a couple months ago on equivariant annular Khovanov homology. So I'll just start by saying the outline. I'll talk about equivariant link homology for links in 3-space. Then I'll talk about the annular theory for links in a solid torus. Then I'll say how to put these together, or one way to do it. And then I'll mention some properties of it. So let's start with the various link homologies. So I'm going to review 3 Frobenius algebras and the tqft that corresponds to them, and following mostly these 2 papers, which kind of summarize some of these Frobenius extensions and some of their properties. So pretty much everything I say is in one of these 2 in this section. So the first one, I'm going to denote R null, A null, and this is just the most familiar one, just Khovanov homology. The second one, I'm going to denote R and A, and I'll explain what all of these are. So R and A, and this is what's called U2 equivariant theory, or also sometimes called universal theory. And then the most important one for this talk is this R alpha A alpha, and this is so-called U1 cross U1 equivariant theory. And I'll explain what the words equivariant mean in this context as well. So each of these tqft's are graded. So they take values in the category of graded R star modules. The star means whatever the decoration is of the ground ring R here. They're all graded. So to get link homology, you take a link diagram, you form the cube of resolutions, or really what I'm thinking of is the Barnetton complex, and then you apply the tqft to this chain complex. Now you have something in module category and you can compute homology. But this, what I'm denoting, this bracket D, is kind of already an invariant of the link. So you need to find tqft's that factor through the Barnetton relations, and all of these happen to. I won't spend much time on that. So this is what I said. So applying each of these to this chain complex, the formal complex, cube of resolutions gives you link homology, something that's invariant under Rademeister moves. And all of these can be extended to cabortisms with dots, all the tqft's, and I'll come back to that later. That's going to be a more important point a little bit later, these dots. And like I said, all of these are graded. So if you have a cabortism S and you have D dots, then all of these are going to associate a map of this degree to it. And again, I'll come back to this later. So here I'm using this grading convention, so a dot is going to have degree 2. I'm going to be using my cursor a lot. So, okay, so let me get into these. So the R null, A null, the most familiar one. The ground ring is Z, the algebra ZX mod X squared. So here's Comultiplication if you'd like. So be familiar. And in all of these cases, so the algebra is going to be a free module over the ground ring, and it's going to have some basis, 1 in X. I'm just picking this basis in this case. I'm going to define the grading by declaring that the degree of 1 is -1, degree of X is 1. So there's 2 conventions maybe that appear in the literature, and I'm using this one. I'll use this throughout the talk. And I want to stress this is the one that's like in the algebra. The ground ring is in degree 0. And when I write deg, I mean like quantum grading, really. So this is the quantum grading. Okay. So I'll let F denote the tqft that corresponds to this. So this Frobenius algebra, Frobenius pair. And if you want to get Khovanov homology, you can apply, one way to do it is to apply this tqft F to the cube of resolutions, and you have the chain complex abelian groups, or graded abelian groups. And this business with the dot is you extend this tqft to surfaces with dots by viewing a dot as multiplication by X. So the degrees multiplication by X is going to be degree 2. So in all these cases, a dot is multiplication by X, as usual. So now this pair RA, it's not going to be so important for us, but I want to say a few words about it anyway. So ground ring is this two variable polynomial ring, variables E1 and E2. Here's the algebra. It's a Rx mod this quadratic polynomial. So you have this defining relation. So here's multiplication for anyone who's interested. So here the ground ring is going to have some non-trivial grading. So E1 is going to be degree 2. E2 is going to be degree 4 in the ground ring. And as before, A is free over R with this basis 1 in X, and here the quantum gradings of those. This is in some other literature, maybe this is more familiar notation with E1 lowercase h and E2 t or negative t with the defining relation like x squared equals hx plus t. Maybe this is more familiar, and I'll explain why this E1 and E2 is more natural here. And the word equivariant comes from this fact that R and A are the U2 equivariant cohomology of a point and of CP1. So U2 acts on CP1 naturally, of course. So that's what the equivariance is from. Okay, so that's all I'm going to say about this for now, and move into the more relevant one, this R alpha, A alpha. So the ground ring is again two variable polynomial ring, variables here, alpha null, alpha 1. The algebra is similar to before. You join X and you mod out by quadratic degree 2 polynomial, but here it splits. So you have two linear factors with the distinct roots. And comultiplication, just adding it here. So again, the ground ring is has some grading, and here both the variables are degree 2. And okay, this is just repeating as usual, but this will always be the case. So A is still free over R with basis 1 in X, and here are the quantum gradings. And here I'll give this tqft a name, we'll call it F alpha. So we had F for just the usual non-equivariant theory, and here I'll call this F alpha. And in this case, R alpha and A alpha, this should be an A alpha here. Should be R alpha and A alpha. So these are the U1 cross U1 equivariant cohomology of a point and CP1. So U1 cross U1 sits in U2. These are the equivariant cohomology. And yeah, so these extensions and some others were studied in this paper from this year, and a lot of what I say is taken out of this paper. Okay, so those are the three theories. Here's some relations among them. So here I kind of gathered them all. So here's like Khovanov, SL2 homology. Here's this U2 equivariant. Here's the U1 cross U1 equivariant. And both of the equivariant ones specialize to this R null, A null, just by setting the variables equal to 0. You can see that clearly. But RA, it specializes to the Lie deformation by you set one of the variables equal to 0, E1 equal to 0, and you set E2 equal -1, then the relation becomes x squared equals 1. So this is the Lie deformation. Once you do that, you can specialize variables in this other way, and you get what's kind of Barnaton's theory. So I'm going to look at this defining relation in A alpha and just expand it. And once you expand it out, you see that these coefficients look a lot like this E1 and E2. And indeed, the pair R alpha A alpha is an extension of RA. You take E1 and identify it with first elementary symmetric polynomial in the alphas, and E2 is the second elementary symmetric polynomial. And you notice that the degrees work as well. E was in degree 2, and so is alpha null plus alpha 1. E2 was in degree 4, and then alpha null alpha 1 is in degree 4 as well. So this is really an extension where you just kind of introduce formal, you allow this polynomial to split.
If you take alpha 0 or alpha 1 or E1, E2, and is there a notion of genericness such that if you're in generic case, then all of them are isomorphic or something like that? Or is each specialization actually going to give you something different?
If you specialize them to numbers, or?
Yeah, if you specialize them to numbers. is each specialization really going to give you something different, or all the generic something? There's a notion of genericity.
Yeah, so I'm not sure. I mean, I know like the lead deformation is very different from like the generic one, for example, but I'm not sure in general. So like this specialization here is different from if they were like formal variables like this. I'm not sure if that answers your question.
Sure, like I guess what I'm saying is that maybe there are some specializations that are just special, but maybe that there's like a generic alpha 0, alpha 1, and you're going to get like isomorphic link homology groups for all of the guys who are generic. But maybe we can answer it afterwards.
Actually, yeah, I'll say a little bit more about that in a minute. Well, I'll say something that might help answer that question. Okay, so well, I'm going to say it right now. So I'm going to focus again on this R alpha A alpha extension, and it has this nice property that I want to explain. So consider the discriminant, this curly D of this quadratic polynomial, alpha null minus alpha 1 squared, and you take these extensions, R alpha D, A alpha D, obtained by inverting this element. So what I mean, just invert the element in the ground ring, and then you extend the scalars in the algebra. And what happens here is there are now these very special elements, lowercase e null and lowercase e1, in this extended theory once you invert the discriminant. So the subscript, like e null, matches the subscript of the variable in the numerator, for example. And why are they special? Well, first, here they form a basis. So that's one reason they're good. So they add up to 1, they're complementary. They're also idempotents, and they're orthogonal. So they're so what these elements allow you to do is to decompose the algebra structure as just a product like this. And similarly, the comultiplication I took this word decouples from this. I like this word for this. What happens here? So I took it from their paper. So it also decouples. It's kind of like a kind of diagonal, maybe. I'm not sure what a good word for this is, but you see that the comultiplication is very simple, and it's also kind of important that these coefficients are units. Once you invert the discriminant, these coefficients are units. So now I'll let f alpha d be the tqft that you get from this, and it determines link homology like I discussed, and it's essentially the lead deformation. And what I have here in this line is, in some papers like Lee's paper and Rasmussen's paper and probably some others, there's these A and B elements, and this E null E1 play the role of that. So if you've seen that, like these E null E1 play the same role as this A and B. So what I mean by it's Lee's theory. So if you take an n component link diagram and consider the chain complex that you get from this tqft, its homology is free of rank 2 to the n. So this is what happens in Lee's deformation as well. And you can, like, the ideas to prove this are in this paper, Barnaton and Morrison, or in Stefan Werley has a paper. The very final remark has an argument for why this happens. And I have references at the end here if anyone's interested. Okay, so now I reviewed some of these equivariant link homologies, these 3 Frobenius algebras, maybe like 3.5, the one you get by inverting the discriminant. So now I want to talk about annular link homology. So the history is, so Sayada, Pruditsky, Sikora define homology for links in interval bundles over surfaces. So they really did it for framed, unoriented links, but I think you usually can just translate between that and oriented, unframed links. Anyway, the special case of the thickened annulus, so the annulus cross an interval, is known as annular Khovanov homology or annular APS homology, sometimes sutured annular Khovanov homology. I think I'll just say annular homology. So that's kind of the subject of this talk. So I'll let this boldface A denote the annulus. S1 cross I, and I is the unit interval. A link, so here's the thickened annulus, A cross I. So a link in there is an annular link. So these are the things we're going to be discussing. And the diagram for an annular link, you get it by projecting onto the first factor onto the annulus. So everything is drawn in the annulus. So I'm going to describe how to get this annular homology, how to get the chain complex. So the first step is just form the cube of resolutions as usual. You just draw the smoothings in the annulus. And this is already an invariant in like Bernotan category of the annulus if you'd like. But you want to apply some tqft to this to land in a category of modules. And I'll still use this bracket D to denote the cube of resolutions, except now it's drawn in the annulus. And finally, to get the chain complex, you apply this annular tqft, and I'll describe how it's defined after this slide. One thing I'll say now is the annular homology has 3 gradings. You have homological and quantum grading as usual, and you have this additional 3rd grading that comes from going like around the hole, so to speak, around the annulus. And I'll explain what I mean by that. So it's triply graded. Okay. Oh yeah, so here I'm just gonna, some convention that I use. So embed the annulus into the punctured plane in some way, like this. Annulus is drawn in blue, and there's the puncture, indicated by a cross. So all your diagrams are drawn in the interior of this, between these 2 blue circles. And I'm just going to draw the puncture. I'm not going to draw the actual boundary components of the annulus. So I'll just represent A just by the puncture, so like this. So I won't have these boundary components. And so here's a annular link diagram. So just the puncture. So this is just the convention. Simplify some pictures. Okay. Okay, so now I'm ready to talk about the actual annular tqft. So this is what you apply to your cube of resolutions that's drawn in the punctured plane. So first thing is that in the annulus, there are 2 kinds of circles. There's the trivial circle, which is contractible, or an essential circle, which is not contractible. And this is an important point. So I'm trying to define this G. So let script C be a collection of disjoint simple closed curves in the annulus. So this is something that you see like at a smoothing of a link diagram. This kind of curly C, and I'm going to define G of C as follows. I have to define it. It's going to be to define it as an abelian group, and I'm going to have to describe the annular additional grading as well. So just as an abelian group, you just apply like the usual Khovanov tqft. So what I mean is kind of forget the puncture just briefly forget the puncture. You just have some circles in the plane, and you just apply the tqft to it. So F, if you remember, or if you don't remember, is just like zx mod x squared. And so that's going to give you a bunch of tensor factors of this Frobenius algebra A null, which is zx mod x squared. And these brackets mean the number of components in C. Okay, so that's G of C as an abelian group, and it has the quantum grading that's inherited from F, from A null. And I'm going to define the annular grading, and here's how it works. So you look at each tensor factor, and if your tensor factor corresponds to a trivial circle, you set the whole thing to be an annular degree 0. All the elements, so that factor is concentrated in annular degree 0 for trivial circles, which maybe makes sense. On the other hand, if you have an essential circle in your script C, in your curly C, you set the generators to have non-zero annular degree, and it matches the quantum grading actually. So I'll use ADEG for annular grading. So for a circle that goes around the annulus, the module assigned to it, it's going to have a generator in annular degree -1 and an annular degree +1. That's for the essential circle. Okay. So here's it. So it's bigraded. That's what I was saying. So bigraded via deg, which is like, maybe I should have written qdeg, this quantum grading, and adeg. And that I might use this order later. So adeg is always second. It's bigraded. Okay, so I define G on circles in the annulus. Now I have to say what it does on cabortisms. So take a cabortism. So let S in the thickened annulus be a cabortism from some collection of circles C1 to some collection of circles C2. So again, kind of forget like embed this solid torus into R2 across the interval. So forget the annular structure and just just apply the F. So that's going to give you a map like this. And what Roberts observed was that this map is non-decreasing with respect to the annular grading. So if you have your cabortism and you just compute it as you normally would, and then you look at what happens to annular grading, it's non-decreasing. And I quote Roberts here because this is not how I'm describing it now isn't how APS originally constructed all their homology theories. This is kind of a reinterpretation. And what I'm describing is really due to Roberts. So it's non-decreasing, and you let Fs sub null denote the part of Fs that preserves the annular grading. And that's what you're going to define G of S to be. You're just going to take the portion where the annular degree is preserved. And I'll give an example this later, if you like. In other words, just so the annular degree induces a filtration, F respects this filtration, and you take the associated graded. Here's some notation. So we'll distinguish the module that's assigned to a trivial and to an essential circle. So for a single circle in the annulus, I'm going to use the notation A null for the contractible, for the trivial circles, and I'll write it as V for the essential ones. They're really, as bigraded modules, they really are different. So I'll use that. And so for example, if you have a bunch of circles, you have n trivial and m essential ones, then the module might be written like this. So you have n tensor factors of A null and m of V. And I'll also use a different notation for the generator, for the kind of standard basis in the essential circles. So I'll use V minus to be 1, and I'll write V plus to be x, and the subscripts match the grading. Here's a graphic that might be helpful. So I'll use 1 and x for the trivial circles. So those are in annular degree 0, and then V minus V plus are on this diagonal. Anyway, so that's how the annular tqft is defined. You take the degree preserving part of the usual Khovanov differential. Let me do one example. So in the thickened annulus, there's different types of cabortisms. It's not just merge and split. You have kind of more variety here if you're also thinking about whether the boundary components are contractible or essential. So here are the 4 saddles which involve at least one essential circle. And these are the only ones where the differential changes, where this tqft has the potential to change. So recall this notation, V minus V plus for the essential circles. So I'm just going to compute this very first one, this A. So it's going to, I'm reading these from bottom to top. So here's the map. So in the first 2 lines, there's no surprise. 1 acts as a identity, so nothing weird here. So really I want to pay attention to this third line. So what does x want to do to v minus? So v minus equals 1, so x wants to send v minus to v plus. But that changes the annular degree, that increases the annular degree. But that changes it, so normally there would have been an x instead of the 0 in the third line, but that's killed once you forget the portion that increases the annular grading. All the other lines are the same. And what you see from this is that x acts trivially on any essential circle. So that's a feature of this annular theory. And so x acts by 0 on all the essential circles, and that's represented by this pictorial relation. So it factors through this kind of relation. It's not exactly local, but if you have a cabortism with an essential boundary component and the cabortism carries a dot, that's just going to be 0. But a lot of maps are 0 in a sense. And I mean, it kind of has to be that way just by degree reasons as well. There are no maps of this. There are no endomorphisms here of the appropriate by degree for what this map has to be. And this kind of relation can hold in equivariant theories just by this relation. If this dot was 0, then 2 of these dots were 0. Then both of these terms would get killed, and you'd left with E2 equals 0, and that's just no good. Or E2 is acting by 0, I mean. Okay. So, very good. Okay, so I'm gonna do this slide and then I'll take a break. So why did I bring up the U2? Why did I bring up these two equivariant link homologies? I want to give a reason for why the U2 one, maybe the more familiar one, doesn't really work with the annular homology. So that's the content here. So here's the U2 equivariant pair, ground ring, this defining relation in these degrees. Okay, so all the variables are going to be in annular degree 0. They have like the quantum grading, but they don't change annular grading. So suppose you're trying to build a theory, like an annular homology using this, this Frobenius algebra in some way. So suppose you have a candidate for what's assigned to this a single essential circle. So you have some bigraded free rank 2 R module with basis m minus m plus in these bidegrees. And you're thinking of this as the module assigned to an essential circle, and let G denote whatever map might be assigned to this cabortism. And you see that for degree reasons, G of m minus, for example, has to look like this, just for degree reasons, because this cabortism should be by degree 2, 0. So that's the only option. And then you look at this relation that comes from the defining relation in A. If you do G twice, you're going to have 2 dots, and you simplify using this relation in A, and you get this equation, and then it's just not going to work because you're going to have this E2 term left. So this is kind of not, you'd have to try something maybe very exotic, I don't know. But so this is an obstruction. And the reason I brought up the U1 cross U1 equivariant version is that gives you more flexibility, and there you can actually build this equivariant annular homology. So that's what I'm going to talk about next, and maybe this is a good time for a break then. How about that?
Perfect timing since we are at 1:30. All right, so as Ross said, we're going to take a break. This is a kind of a new thing we're doing in the seminar just for everybody to absorb everything that they're learning right now. Of course, Ross is still on the hot seat and could be asked any questions, but if you need to go like get a break or something, like that's fine too. So let's re-adjourn at 1:36. Do whatever you need to do.
Ross, can you briefly go back to the slide about the Robert filtration? Yeah, so maybe just, can you briefly remind me what annular grading is?
Yes, so that's on the previous slide. So you have a bunch of circles in the annulus, and each one of them contributes this A null to the module.
Mm-hmm.
And for a trivial circle, the annular grading there is entirely just 0.
Yeah, yeah.
If it's an essential circle, then those generators have annular degree equal to their quantum grading, for example.
Yeah. And then you take the you take increasing or decreasing filtration.
Yeah, that depends on, let's see. So here it non-decreasing. So you take this, you take, well, I mean, one of them works like.
So when you take some kind of adjoint map, and you get an invariant of kind of cabortisms in the annulus. So you take the kind of the adjoint map under this filtration.
You could just take this degree 0 part. So the map FS splits as a part that preserves, it's a sum, part that preserves the degree and part that strictly increases it. And you just take the degree 0 part. And this is functorial as well. That's one way to think about it. I mean, that's how I think about it.
But I guess for any commutative Frobenius algebra, right, it gives you 2D tqft. You can ask for kind of what sort of filtration can you get to get a tqft in an annulus, right? So if you just have a commutative Frobenius algebra,
right,
for the properties of filtration on this algebra to get, so that if you pass to the associated graded theory, you get the theory in the just the usual tqft in the annulus.
Yeah, of course. And you have to check these.
In the background, you have a map into S1. It's sort of a tqft with the background k pi 1, kz1. You have a map into kz1 that's in the background.
You just mean because they're in the solid torus? So
Yeah. Because I mean, if you're just looking at the 2D tqft, you kind of you don't care about embeddings. You just it's a cabortism, but in this case you have a map kz1.
Here,
or maybe even less, because you don't. Oh no, it's less.
No, here it doesn't depend on the embedding, really.
It's not kz1 because you don't have all the maps. You just have circles that go around once or contractible circles. I take that back. Thank you.
Hey Ross, maybe this is already obvious and answered. I'm not sure. I'm blanking right now. Is there an odd version of all of these equivariant types? Equivariant homology theories?
I don't know. I don't know really much about that.
Okay.
Yeah, maybe somebody else can answer.
I don't know. Yeah, it all seems very natural, and I just like want to know what the construction would be. Okay, so
I'm not sure. I'm trying to remember if I've seen this, but nothing comes to mind.
Okay. Okay, so it's 1:36. Let's keep going. As a reminder, if you have a question, Ross would like you to just speak up. If you do type it into chat, I will interrupt Ross and ask him a question. Okay.
Great.
Carry on.
So now I'm going to define the equivariant annular tqft, and I'm going to call it G sub alpha. Okay, so let's go. So here's a reminder of what the these Frobenius algebras. So you have ground ring, two variable polynomials. Here you have the algebra or this defining relation splits, and the alpha null, alpha one are in degree 2. So, okay, we'll define this tqft. It's going to be bigraded as well. So this is what I mean, z squared graded. So one key thing to realize here is if you have essential circles in the annulus, there's I wrote naturally ordered. There's like one of two natural ordered. And from innermost to outermost, for example. So innermost, so here you have some essential circles in the annulus, and you start closest to the puncture. And that's the first one, then the second one, and so on, like outward. So this is going to be an important point, this ordering. Okay, so we're defining this G alpha. So take a collection of circles, something that you see in a smoothing of a link diagram. So just as a module, so this kind of parallels the construction I explained earlier. As a module, just apply this this F alpha, this tqft associated with the R alpha, A alpha. So this is module structure. It's going to have an additional grading. So that's the new information. We'll define additional grading on this module. And okay, so here's how this works. So both of these sets are bases for A alpha. You can take either 1 x minus alpha null or 1 x minus alpha 1. These are homogeneous with respect to just deg, the quantum grading. I haven't defined the annular grading yet. So, but they're both bases. And I'm going to introduce this notation. So I'm going to, similar kind of to, I'll use V's with some subscripts for essential circles. So I'm going to have V null and V1, and I'm also going to have V null prime and V1 prime. Okay, so V null and V null prime are the same element. So I have two notations for the same thing, but this is going to be convenient. And so both V null V1 and V null prime V1 prime are bases. And for these elements, I'll give them some degrees. Again, matching the quantum grading. So the degree of V null and V null prime minus 1, the annular degree of those. Annular degree of V1 prime equals positive 1. Okay, so with this notation, so now I'm ready to explain the annular grading. So the tensor factors in this module coming from it corresponding to a trivial circle, those are all in annular degree 0 as expected. Now here's the important point. Factors corresponding to essential circles are given homogeneous bases, either V null V1 or V null prime V1 prime in an alternating manner, depending on the nesting, the parity of the nesting of the essential circle. So the only thing that switches between these two bases is it switches between like x minus alpha null and x minus alpha 1. So there's this alternating thing that happens. And so what I mean, like, so the very first essential circle, the one closest to the puncture, you give it this, I said bihomogeneous, so homogeneous with respect to the bigrading, Qdeg and Adeg. So the first one, the innermost one is assigned this basis, the second one is assigned the other one with the primes, and then the third one is assigned V null V1 again, so it alternates like this. So that's the key point, this alternating assignment. So here's the proposition. So let S in the thickened annulus take a cabortism S in the thickened annulus from some collection of circles C1 to a collection of circles C2. If you view S as a cabortism in 3 space, and just compute the map assigned by this tqft F alpha, you just compute it as you normally would, and you just check that it doesn't decrease the annular degree either. So this is a computation. And you define, as before, you define G alpha on an annular cabortism, say S, by just taking the degree 0 part of F alpha of S. So by the proposition F alpha of S is a sum f alpha s of 0, which preserves annular degree, and some term that strictly increases it. And you just remember the one that preserves it. So setting the variables equal to 0, you just get back g. This is clear. You have maybe some other specializations. You can set one of the parameters to 0 and rename the other one to h. And this is like Barnetton homology. I mean, but the important point is the G alpha. Okay, so I think, so I'm not going to do the calculations for this proposition, of course, but I want to give the key examples. So this was like, this is really the cabortism you want to look at. We'll let S denote this cabortism, so it's a product on an essential circle with a single dot. And recall the notation I'm using, V null V1. So I'm going to compute what I'm going to compute what G alpha does to this cabortism. So I'm going to start with F alpha, and what does the dot want to do to V null? So it wants to send that to X, right? So to see the part that preserves or increases the annular grading, I want to write this in terms of the homogeneous basis that I've chosen. So I rewrite X like that, and then this first summand, X minus alpha null, is exactly my basis vector V1. This alpha null, like secretly it's like times 1 is this term. And the term that I boxed is the part that where the annular degree got increased. So it went from V null to some multiple of V null. Remember, the alphas are an annular degree 0. All the variables are an annular degree 0, so they don't change that. They change the quantum grading. Anyway, so this V1, it's bumped up from V null. Okay, and if you compute what F alpha does to V1, you just get this. There's no extra terms. So the box term is where you see this jump in annular grading. So then this is the map. You just delete the box term. You only remember the terms where the ADEG is preserved, and here's the map. So the dot multiplies V null by alpha null and multiplies V1 by alpha 1, which maybe explains the notation V null V1 in this for these elements, but there's a lot of zeros and ones. So this is one of the key examples. So oh yeah, right. So here's the more general example. So consider this cabortism. So you have M essential circles, and you just take the product of those, like the product cabortism, and the ith component carries a dot. All the other ones are undotted. So try to illustrate that here. So this is kind of more general than the previous example. So of course, the map assigned to this, G alpha of S, it's the identity on all the tensor factors except on the ith one. And you compute it on the ith one, it's gonna have one of two forms depending on the parity. So if I is odd, so like if I is equal to 1, that's kind of what we did before. It acts like this. V null goes to alpha null V null, V1 goes to alpha 1 V1. If I is even, this switches. Now the lower annular degree vector, V null prime, gets multiplied by alpha 1. And the higher annular degree or element gets multiplied by alpha null. And that's how this cabortism acts. So the action of the dot depends on parity. I'll say a word about this later. Oh, okay. So these are two kind of key examples, and here's another one. Like I said, you would check four different saddles. So let me kind of show one of them. So here's this saddle. Sorry, it goes from 2 essential circles to 1 trivial circle. So you multiply them, multiply the 2 essential circles, and you get this trivial circle on top. Here I'm recalling my notation, and you just compute the map. There's nothing happening here. So V null prime, and you have to multiply them. So you're multiplying 1 and 1, you're going to get 1. But this the left-hand term is an annular degree -2. So this term is going to have to, but this term is in degree 0 because it's in a trivial circle. So that's going to have to get killed. All the other terms, nothing kind of, there's no annular degree jump, but I will point out this in this very last multiplication, V1 and V1 prime, when you multiply them, you get 0. That's the defining relation in A alpha, that x minus alpha null times x minus alpha 1 is 0. And since these are on consecutive essential circles, those are the basis elements there. And I wrote that here, this kind of merge, anytime you merge two essential circles, they always have to be consecutive in the ordering. So they're all, like, essentially this calculation is the only one you're gonna have to do. Or if you flip this cabortism around and you have a trivial circle splitting into two essential ones, then those are all, always gonna be consecutive, of course, and so on. And I'm not gonna show the rest of the calculations, but it's not, you just have to check. So I wanna give a couple remarks about this tqft, in this parity issue. Maps assigned to cabortisms can be kind of guessed in a sense. I'll say what I mean by that. So you could try to look for this U1 cross U1 equivariant version of annular homology and try to see what the cabortism maps, like the saddle maps, ought to be. So consider this cabortism, which we considered several times now. And so just like similar kind of thing that came up earlier, so take some bi-graded free rank 2 module with basis and these bidegrees. So you're thinking of what is this theory assigned to the essential circle, and I'm calling it M. And this is kind of like the obstruction, the U2 obstruction that I described earlier, but it's not an obstruction in this case, of course. And you just compute what could the map be. What I mean is, like, what map could S be assigned? And you look at the bidegree considerations, the map ought to be bidegree 2, 0. You consider that, and that gives you some conditions on what the map could be. You also look at this relation, this defining relation, and that gives you some other conditions on what the map can be. And I think at this point you have 4 options. And then the alternating phenomenon, you could already have guessed based on considering this cabortism. I'm not going to be super precise here, but if you consider this cabortism without the dot, then you don't really have a choice for what that's, without the dot, you don't have a choice for what map that's going to be. So now with the dot, you kind of have 2 places to put it. You can put it on this innermost one, or you can put it on the outermost, like near the outermost essential circle. I mean, these are the same, you can slide the dot around, but this will give you an idea based on the previous conditions or restrictions that you noticed what the map could be for S. So what I'm saying is that one in theory could write down these maps, but proving it's well defined is difficult. But with this filtration, it's essentially immediate. But you have to come up with the filtration. That's one comment I wanted to make. And the other is unrelated to what's the other stuff in the slide. Grigsby, Khovanov rarely show that the annular chain complex, not the equivariant one that I'm talking about now, non-equivariant one, has an action of SL2. So there's a action of SL2 that commutes with the annular differential. So that's something specific to annular homology. And the action also depends on parity of nesting on the essential circle. So SL2 there is going to act trivial by 0 on the trivial circles, and the essential circles, it's like the fundamental representation, but there's the sign that comes up based on parity of the nesting. So that this kind of alternating idea is shown up elsewhere, is the point I'm trying to make here. And then in the last 4 minutes, is that right?
Yes.
Okay. I'm just gonna, I'll just say one additional property of this equivariant annular homology, going back to inverting the discriminant. So we talked about this before, and I'm recalling it here. Here you have this element D, and you have R alpha D, A alpha D that you get by inverting D. And that gives you these special elements, E0, E1, that form a basis and are orthogonal and decompose or decouple the Frobenius algebra structure. And the homology is kind of determined by the number of components and the linking number. And I'll let G alpha D denote the annular tqft that you get by extending scalars. Just extend scalars everywhere. You just have this D inverse. And the theorem is that the same thing happens. So if you take an n component annular link with some diagram D, and you let this denote the chain complex that you get by applying G alpha D to cubic resolutions, then its homology is again free over R alpha D of rank 2 to the n, the number of components. And I'll explain very briefly why that happens. Essentially, this chain complex, and the chain complex you get by forgetting the annulus entirely are isomorphic. It's a kind of interesting thing that happens. Okay, so now I'm going to introduce just very quickly some more notation. So I'll use these bars, V null bar, V null prime bar, and so on, to denote certain elements of A alpha D. So now I have 4 notations for the same element here, but again, it's just convenient. And those are unchanged from the elements without the bar, but V1 bar and V1 bar prime are slightly different. I divide by this element. So now these on the right-hand side look like E0 and E1. And okay, so I'll just say what's on this slide. So I look at these 4, you would look at these 4 cabortisms and see what the maps are with respect to these new bases with the bars. So let's look at this first cabortism A. If you just focus on the first cabortism, the first map here on the left, you'll see that there's this orthogonality thing happening and this idempotent thing happening. So what I mean is written here. So from A, you see that V null bar acts like E1. What I mean is, if instead of V null bar here, you put E1, then you'd get that these 2 elements are orthogonal like you'd expect. If instead of V null bar here, you'd put E1 and you put E1 here, then you'd get that it's idempotent, and so on. And then V1 bar acts as E null as well. So some mismatch with the subscripts. And it's kind of flipped for the elements with decorated by primes, but essentially with respect to these elements, the formulas are exactly the same as if you forgot the fact that the cabortisms are in the annulus. And the same thing happens for these split cabortisms. So V null goes to V null tensor E1, and V null kind of acts like E1. And so there's no difference in the chain complexes besides the annular grading. And that's all. Thank you.
Thanks, Ross. Let's thank the speaker. Okay, are there any questions for Ross?
Ross, a very nice talk. Can I ask you on the last 2 slides, are you sort of saying that around the puncture, the theory behaves like this theory and it's semi-simple, but away from the puncture, it behaves like the usual theory and it's not semi-simple?
I'm not sure. To me, it seems like it behaves like the Lee version of just.
But it's sort of like saying that around the puncture, it's, let's say, the theory, but away from the puncture.
Away from the puncture, it's the same with these E nulls and E1s.
Well, but I would guess, I mean, away from the puncture should be just the usual theory, right?
Of course, that's right.
But are you saying that kind of around the puncture, it's a sort of a least theory?
Yeah, that's right. That's right. Yeah. It like here, so like E null is x minus alpha null. X acts as alpha null on this element, so it's 0. You can, but yeah, here up to like renaming the basis, it seems to me that there's no difference between the chain complexes.
Wait, but on this slide, you already inverted the discriminant to get V null and V1 bar, right?
That's right. Yeah.
So that means outside, like away from the axis, the puncture, you still have the inverted discriminant.
That's right. Yeah.
Right? So wouldn't it still be a Lie theory away from the? Okay.
That's right. Yeah.
Yes. So maybe also, can you repeat that? So maybe I'm confused here. So maybe what I said doesn't make sense. So around the puncture, you don't actually have a sort of kind of multiplication, right? You can multiply around the puncture with away from the puncture, but not, well.
Yeah, it's not.
Yeah.
I'm not sure what the word for this kind of thing is.
Yeah, I mean, all I was saying.
But you have this nested collection of circles one inside the other, and you can kind of merge two consecutive circles into a constructible circle.
Yeah,
so multiplication is kind of restricted in this sense.
That's right. I mean, it's a module over the trivial circles and a co-module, but it's not algebra itself. You can only merge into a trivial circle, like you said.
Hi, Ross. Great talk. I don't have a precise way of saying this, but are you familiar with the two-color temporal weave algebra?
No.
It's like a stupid thing. You take a temporal weave diagram and you shade a region either red or blue, and two red regions don't touch, the colors alternate. So there's just two ways of doing it. Either the leftmost region is red or the leftmost region is blue, and that determines everything else. Okay, that's like a stupid extension of the temporal weave algebra. But are you familiar with the sort of dotted temporal weave algebra?
Yeah. Oh, sorry. No. From this, you get dotted temporally Lieb thing, which I didn't talk about, but is in the paper. But I'm not sure what you're referring to.
Well, so in a theory called geometric Satake, the sort of two-color temporal Lieb category corresponds to, well, something complicated in geometry, but it corresponds to certain morphisms between bimodules over polynomial rings. And the temporal Lieb diagrams themselves are just the degree 0 morphisms. And when you start adding dots, you get these higher degree morphisms. But the point is that this is a polynomial ring in two variables, alpha s and alpha t, corresponding to the simple reflections of the affine wall group. And these sort of alternate, and sort of the meaning of the dots should really alternate. And this looks a lot like sort of how you've constructed what goes on with your annular, with your essentials.
Yeah, that's interesting. I didn't talk about this here. If you take a temporal Lieb diagram with some dots, what you can do is spin it around in the annulus, cabortism, and then you decorate the component by a dot if the tangle component had one as well. And then using this tqft, you get a map assigned to that cabortism. So you can interpret dotted temporal Lieb diagrams using this as maps between tensor powers of A alpha. But I don't know, I mean, it'd be interesting to learn about what you mentioned.
Right. It certainly has connections to things that knot theory is also supposed to have connections to.
Actually, I have a question for Ben. So do you see in that theory on the Satake side the universal developing algebra tensored with the polynomials over symmetric polynomials, where you identify symmetric with the center? So do you see modules of this bigger universal developing algebra?
So which in developing algebra of what?
You just take a simple, I mean, SLN, take SLN, take its universal enveloping algebra, take the center.
We're doing SL2 right now, basically.
SLN or SL2, yeah, it doesn't
Okay,
matter.
all right.
Take SLN. So take the center, tensor it with polynomials over. So tensor universal enveloping algebra with polynomials over symmetric polynomials. Is that the same as studying certain kind of modified theory of modified sheaves, like what you guys call monodromic?
Right, you're describing something like the deformed category O.
Might be similar. I mean, I'm not sure what you mean by deformed O.
Yeah, deformed O is constructed in the same way, and that's basically what simple bimodal study. So,
Okay, let's go. So what's a reference for deformed O?
oh man, Roman Bezikov taught a class on it, and Tina Konstop took some notes. Tina, do you know? I saw her here earlier. Maybe she's gone already.
But so this is called deformed O.
So if you take category O and tensor over symmetric polynomials, which is like the center of the enveloping algebra.
Yes, yeah. We call it
polynomial, you get something called deformed O.
So this is probably very similar to what's going on here.
Yeah, and it's got translation functors and it has all this wonderful stuff. It's a really nice way of understanding everything, including circles theories.
All right, I think this is a natural lull in questions. For the sake of the recording, I'm going to just say, let's thank the speaker again. And if you still have questions for Ross, then you can stay after. So let's clap for Ross.
Thank you.
Okay.